A coil with 45 turns is wound around the solenoid with 320 turns and of length 26 centimeters. The radius of the solenoid is 1.2 centimeters. At a certain time, there is a current in the solenoid equal to 0.14 amps, and the current is increasing at a rate of 1.6 times 10 to the third amps per second. First, we calculate the average magnetic flux through each turn of the solenoid. The magnetic field inside the solenoid is uniform, so the flux is equal to magnetic field times the cross-sectional area times cosine of the angle between the magnetic field vector and the area vector. Because the magnetic field vector is perpendicular to the cross-sectional area, the angle is 0 and cosine 0 is simply equal to 1. Now, what is the magnetic field equal to? For this, we are going to use the formula for the magnetic field due to a solenoid. And the area is a circular area, so we will substitute pi r squared for the area. Here I have substituted the formulas for the magnetic field magnitude and the cross-sectional area. Next, let's substitute the numerical values and calculate. Keeping two significant figures, we get 9.8 times 10 to negative 8 Weber for the average flux through each turn of the solenoid. Now let's calculate the mutual inductance between the coil and the solenoid. Here's one formula that we can use to calculate the mutual inductance. It's equal to the number of turns in the coil, that's N sub 2, times the average magnetic flux through one turn of the coil, divided by the current in the solenoid. It turns out the average flux through one turn of the coil is equal to the average flux through one turn of the solenoid. These two things are equal. Why is that? If you think about it, where does the flux come from? It comes from the magnetic field of the solenoid. There's only magnetic field in the solenoid, and the solenoid is inside the coil, so the cross-sectional area of the solenoid is smaller. That's the common cross-sectional area between the two. So whatever flux there is in the solenoid, there's the same flux in the coil. So then we can replace the flux for the coil with the flux for the solenoid that we have already calculated in the previous part. Next, again, let's substitute the numerical values and calculate the mutual inductance. Again, keeping two significant figures, we get 3.1 times 10 to negative 5th Henry for the mutual inductance between the coil and the solenoid. Finally, let's calculate the EMF induced in the coil. For that, we can use the mutual inductance and the time rate of change of the current in the solenoid. So the EMF induced in the coil is equal to negative M times di dt. When we plug in the numbers, we get negative 50 millivolts for the EMF induced in the coil, keeping two significant figures.